What is this high resistance neutral grounding? You're able to hear, right?
Yes, sir. Now I can hear.
The screen also. Okay, thank you. So what is this high resistance neutral grounding? See, high resistance neutral grounding means first thing in the word itself, everything is there. It is something
Yeah.
related to high resistance, right? So what is high
Yes.
resistance? As I go further, I will tell you what is that high
Okay.
resistance. Because last time I explained about low resistance neutral grounding. So that was
Yes.
mainly for motors. High resistance neutral grounding is mainly for generators, the two big generators. See, you have seen an alternator. This alternator has a neutral. That neutral,
Yes.
we are connecting it to the ground directly. It is called solid earthing. That is what we use in our normally in our small LV system. Whereas in case of our big system, we go for high resistance grounding. So when I say high resistance, we are connecting a high resistor here. Why we are connecting high resistor here? The concept I will tell you. See, first and the foremost, why we do neutral earthing? It is to protect the people. What do you mean by protect
Yeah.
people? If you don't earth the neutral, then see there will be when there is a fault, where will the fault current go? Detection of fault will become very difficult. Tripping of breakers will become very difficult. So I see either you can earth the neutral and use relays, or if you don't earth the neutral, that time you have to use again. It is called unearthed system. In unearthed system, actually fault current will be very less. But what happens in a big distribution system, because of capacitance, there will be charging current. So in reality, there is no system where the fault current is zero. So what happens when you use another system is there will be some current of let's say 1 or 2 amps. That 1 or 2 amps current cannot be detected properly by your relay, and when the 2 amps passes through the person's heart, they will die. So using that is the reason why we use a solid grounded system with relays. So one is function of neutral thing is protect people, protect equipment. When I say protect equipment, basically protect equipment from high voltage. In one of the next slide, I will show you how it protects from high voltage. Now, see the when you draw the sequence component, I will show you in one of the slide. The fault current is basically voltage divided by system impedance. Normally, when we do the calculation, and if you have the earthing resistance, then fault current IF is equal to V divided by X plus Rn. So basically, this resistance will reduce the fault current. So when you see the sequence network, I will show you. And see the why voltage will build up in a system. See, your power system is basically a RLC circuit. It has inductance, it has capacitance. And whenever there is a fault, what happens? The fault is basically an arc, right? Because it is an arc, the voltage across this inductance, capacitance, and the voltage across the capacitance will build up. So to reduce that voltage build up, you need the current to be discharged. So that's why you need a neutral path. So when you don't have a earthing in a unearthed system, voltage will keep on building up during a fault. And we are using resistance earthing, whether in a motor or in a generator. The main reason is we have to keep the fault current magnitude very less. Okay. Till here, any doubt?
No, sir. But in North America, the project, some of the projects that we are working, there even the transformer they are going for high resistance ground, sir, in LV network.
Okay. What is the that is basically when you say high resistance, it is not high resistance, it is low resistance. right?
Actually, sir, the earth current, fault current, the ground fault current, they are limiting it to 5 amps.
5 amps. Okay. So what is the
Uh,
voltage rating?
Voltage is 480 volt.
LV 480 volts. Okay.
Yes, sir.
See, for example, even in mines, they have this practice in our place.
Okay.
And
Uh,
in power distribution system, throughout the world, there is different concept. Some people go for solid earthing. Some people go for resistance earthing. In resistance, some go for low, some go for high. Some go for reactor earthing. Some go for tuned reactor earthing. So in power distribution system, I have actually made a survey. I have a small table. So almost
okay.
each of the country they have developed their own system. But finally, whatever earthing system you use, the protection you have to use accordingly. That's all. If you use North
Right.
American earthing and European protection, you will be under problem.
That will not work.
The insulation design, the earthing design, and the protection design, all three have to be in synchronism.
Okay.
Okay. Now, see, this is our rotor of alternator. See, what is
Yeah.
this made of? You can see it is made of number of stampings, right?
Yes.
It is made of many number of stamping, and each of these stamping, it is very thin, and it is all together punched, and between stamping there is just a small layer of varnish, right?
Yes.
Now what happens when there is a fault in a winding? See, when there is a fault in a winding, the winding will burn. There is an arc, and because of an arc there is a heat, and because of that heat, what will happen between these two stamping? If the varnish, let's say, the temperature is such that the varnish get damaged, and then also let us say there is the arc creates a welding between two stamping, that is a very serious problem. See, if winding is damaged, we can get rebound, but stamping get welded, it is a real problem. Okay. So what are the causes of a fault? One is the insulation is deteriorating over a period of time, and cause of insulation deterioration is again weather, improper maintenance. If you keep subjecting your system to over voltage frequently, let us say you have a 6.6 kV motor, and it can take 10% over voltage or whatever. But if you keep on subjecting to that value regularly, naturally its life comes down. And if you subject to, let's say, instead of 10%, 15% or something, okay, now motors normally we are having our relays, right? Now, see, individual motor we don't provide over volt this one the voltage relay, but for the entire power system we have the voltage based relay. The
Yes.
entire power system voltage when it increases, there are relays which will trip the system. But there is some magnitude of over voltage that is allowed in the system. Now that over voltage, and also over voltage, there is a time period, right? So what happens when the system gets subjected to over voltage for short duration? Maybe it will not get damaged, but life will come down. Okay. And similarly, lightning when it strikes in a building or a factory, what happens? The lightning current may not flow into your switchgear. It may not flow into your motor or generator, but because it has struck your building, there is a ground potential rise. There is a transient over voltage. So what will happen? Your insulation will all undergo some stress. So that stress sometime may damage the equipment immediately, very rare. And sometime what happens? not sometime. Whenever it strike, what happen? Life comes down little bit. In short circuit, yes, this is a real problem. When let's say my generator has a short circuit, your breaker might have tripped. My motor had a short circuit, your breaker might have tripped. But one is whenever there is a short circuit, a big huge current flows in the entire system, and that current again, that current itself is a cause of fault for a future current. Okay, because short circuit is accompanied by heat and also some forces.
So it weakens that area, right?
Yes, it weakens not only that area because current flows from the system.
Mm.
So all the cable feeders, suppose a cable is 1000 amps, it is carrying, or let us say it is a bus duct or something, and if there is a short circuit at some feeder far away, and if 500 amps additional is flowing, that is different. But if the short circuit has occurred somewhere nearby and 1 kA, 2 kA, 4 kA, 6 kA, like this current flows, then that really weakens the system. Then all your electrical equipment are designed for some temperature, and whenever we operate at a temperature higher, then that is also a cause of a fault in the long run. Now, what causes this temperature rise? See, temperature is basically nothing but amount of heat generated minus amount of heat dissipated. The amount of heat generated depends on the I square R loss. The amount of heat dissipated depends on your cooling, your design, ambient temperature, and then how your enclosure is made, whether dust is accumulated in the enclosure. All this comes into account. So sometime what happen over a period of time, your enclosure dust will be accumulated. So cooling will not be effective. So that leads to over temperature. And when temperature rises, gradually your insulation deteriorates. Mechanical vibration. See, if your this one undergoes nearby any vibrating equipment is kept, or let's say you have a motor and the motor and pump. See, if it is not the foundation is not proper, then it will lead to vibration. And when there is a vibration, what happens? The cable which is getting connected to your termination box, so they may become loose. It may lead to small gap. Then their arc may get developed. So mechanical vibration also is a thing. Earthquake is a very important thing. This see actually Earth. If you see what earthquake we see or we feel or we see in the news is very less. But every day, every week, every month, there are lot of small earthquake going on, which we may not feel. They say no Richter scale. They may say that no, there is earthquake of 7 magnitude, 6 magnitude. Those earthquake may be very less, but
Yeah.
very small earthquake keep happening. So these earthquake when they happen, what happen is the entire system will shake, right?
Yes. Yes.
So that and also will basically it will also cause development of what in future. Okay. Then corrosive atmosphere. Yes, this corrosive atmosphere also is a very big problem because see if you go for our what is it in oil and gas industry, or if you go for industry in Gulf or our places where like Chennai or Mumbai or Mangalore, coastal area, you can see corrosion is a very big problem. And most of our refineries are located here. in the corrosive atmosphere.
Yes.
No doubt we
Yes.
are designing our system for that corrosion, but even then, long run, what happens? This corrosive atmosphere is a big problem. It will slowly deteriorate your equipment, right?
Yes.
Okay. Then, as I told, extreme ambient conditions. What is extreme ambient condition? Extreme ambient condition.
Yes,
Saudi. You have worked on Saudi project.
yeah. Yes, I worked in Dammam project, Saudi.
Okay. What is the ambient temperature there?
There it goes up to 50 degrees Celsius.
Okay. Wind speed and all.
Wind
I
speed,
think
I am
more,
not
right?
very sure. No, it is very high. It is very high, and it also has dust particles.
Okay. Because of the sand.
Yes, they have sandstorm. So for that, we need to take a lot of factors into consideration.
Okay. So, as you said, these extreme weather condition, for example, Leh, Ladakh, power grid substations are there. There are these also Rajasthan, Saudi, Siberia. So we have lot of places, and one thing is the extreme weather condition places are the one where we have lot of natural resource also many times. So so electrical infrastructure will be there also. So that extreme is one cause of fault. And dust, just now you told about dust, snow. Okay. So these are this one. Now, type of grounding. What are the different types of grounding? Solid grounding, there is no intentional resistance between the neutral and the earth. And this is what we use in our Indian system, and the low voltage. And even the 220 kV, our transmission line also is solidly grounded only. Fault current will be very high, but over voltage will be limited, and relay coordination is not a problem. Low resistance grounding, we use a small resistance between the neutral and the earth, and this is used for medium voltage motors. Like here we will have 100 amps, 250 amp, 400 amps, and so on fault current.
The grounding actually is done on the generator or the transformer where we have medium voltage motor. Correct, sir?
Yes, system grounding is always done at the neutral. Neutral
Yeah.
will be the transformer or generator. Correct.
Yeah.
Then fault current here we reduce to a value slightly higher than the load current. High resistance neutral grounding is the one which we use for generator. Here the fault current is reduced to a very low value, and as you said, distribution system also, some people may use high resistance, some people may use low resistance, and some people may use high resistance, some people may use low resistance. In distribution system there is a lot of mixture, so I'm mainly talking about the general what is followed mostly. So some deviations are there also. Okay. Now fault current magnitude in high resistance grounding will be very less. Like it will be less than 10 amps. That the reason I will explain later. Okay. Ungrounded system. Have you come across any ungrounded system?
No, sir. No, I have not.
Ship. You have worked on any ship? Mines? Hospital?
No, no, no,
Okay.
no, sir.
Actually,
So
hospital.
there is no grounding at all.
Where?
In ungrounded system, if there is no grounding at all, then how will I understand? Will it be safe for the person?
See, ungrounded system, though there is no grounding, the
Yes.
fault current will go back to the neutral via the charging capacitance of the system. Okay.
Cable.
So
Ah,
whenever there is a fault, the fault current will not flow through your earth to neutral. Instead, it will go via the, for example, see cable. Cable, you have conductor inside. The between each phase, you have insulation.
yes.
So current will flow back through the insulation. That is what is the charging current, right? So insulation will not conduct. How current flows in a capacitor? When we apply AC voltage to a capacitor, it will not conduct like a conductor. Instead, there will be this charges are induced, right, at
Yeah.
the other side. So it's a different phenomenon, but there is a charging current. That is how current will go back through the neutral, and you need lot of extra protection here, and also insulation has to be higher. See, normally in our LV system, we are if it is a 11 kV system, I am taking a 6.6 kV cable, right?
Yeah.
Whereas if it is a another system for 11 kV, I have to take 11 kV cable only. So insulation cost will be higher. So this slide, see, very simple: generation, transmission, distribution. In generation, power plant, we can use high resistance neutral grounding, NGR, NGT. And one more thing I will explain later, we need to have unit transformer also whenever we have high resistance neutral grounding. Then there is one more concept, the resonant earthing. Transmission, we use solid earthing. Any transmission projects you have done?
No, sir. Mostly plant only.
Okay, transmission we are using solid earthing. Distribution means what comes to our houses. We are using solid earthing. Some are going unearth system, and some are going for resistance earthing also. And you told you are using high resistance grounding in North American project. Yes, there are different concepts for in distribution system.
Yeah.
Whereas in transmission, everybody will go solid earthing only. The reason is the relay coordination for hundreds of kilometers we cannot do if we go for other system. This damage energy, see, damage is proportional to arc energy, right? If I'm having a generator or a motor stamping, the amount of damage is proportional to the arc energy. And arc energy, any energy for that matter, is proportional to what? Current and the time. Okay.
Time.
And here there is one more constant tau. What is this constant tau? It is basically the circuit constant. So when you have an arc in some this one, uh, some particular place, that place is finally in a circuit, right? A plant is a circuit, so that constant is this tau. And what is this time t? It is the amount of time I allow the arc. So based on that, we can get the damage energy. See, the understand one thing, the main concept of high resistance neutral grounding is basically to reduce the arc energy or the arc current. Okay. So when I reduce the arc current, my generators and all will not get damaged. Now here, what are the things I can play with in this formula? I can reduce I can reduce T. These are the only two things I can do. I can reduce my fault current. I cannot change my circuit time constant. I can reduce the fault current and I can reduce the time also. Right? I will later on
Yes.
explain to you, time also cannot be reduced. Okay, I will tell you later on. See, If you are having, let's say your plant, your one feeder is going to a motor. Now you want to trip that motor, you can decide when to trip based on the relay setting, right? Instead of 300 millisecond, I can trip at 500 millisecond, or I can trip at 1 second. Whereas in this power plant generator, though my generator circuit breaker is tripped, my fault will still exist for a long time. I will explain about that concept also. Okay. So now you see here, see, this is your generator, right? Winding. Now here there is a fault, okay?
Inside the winding.
Inside the winding. This is a fault inside the winding. Now, when there's a fault inside the winding, what happens? Current will come from winding to stamping, and stamping is connected to the outer surface, right? The yoke. From there, body of your generator is earthed. Fault current will finally enter your earth grid, and from there are two components. One is the component will flow to the system charging current. So you see this current will flow to the system charging current. The other component will flow back via the NGR. See this NGR, see this is a combination of NGR and NGT. NGR and NGT, why we are using? Any idea?
To reduce the current.
Okay, you're correct, to reduce current, but why we are not connecting resistance directly instead of connecting to the transformer?
Maybe the rest. Not sure, sir.
See, actually, that also I will, when we do one or two example, you will understand. Instead of using a 11 kV resistor, I will use a 220 volt.
Okay.
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 That is one thing. And second thing, you will see later on that if I want 1300 ohms resistance, by using a 2 ohms or 3 ohm resistor, I will get 1200 ohms. Okay.
Sir, but here we are only controlling the secondary current, correct, of the transformer.
Which is secondary according to you?
The secondary is the
This one.
this one where we have the resistance.
Oh, you mean to say this? Yes. See, if I reduce this current also will reduce.
So okay.
Because see,
So
a transformer, if I change this, if I change primary, secondary will change. If I change secondary, primary will change. In a transformer,
so relatively, I am reducing there.
The mutual induction, no? Both are linked. So later on, I will explain you how by using a small resistor of few ohms, I will get a resistance here of few kilo ohms. Okay, that is the advantage of using the NGT. See, this resistive component current, this is resistive current, this is capacitive current. Both of these have to be equal, or resistive current has to be more than capacitive current. Okay, why? Any idea why resistive current has to be more than capacitive current? Or
because the capacitive current will definitely be there, irrespective, even if it is not grounded. The minimum capacitance current will be there, so that should not trip the system.
Actually, you are correct. That is correct. See, actually, if the resistive current is more or equal to capacitive current, it will not lead to buildup of voltage during a fault. That is the main reason.
Okay.
Okay. Now, high resistance neutral grounding, we use it not just for a generator, unit connected generator. What do you mean by unit connected generator? There is a unit transformer also.
Okay.
Then, as I told, it will prevent the buildup of large voltage, prevent damage to machine. Then, what is the limit for this high resistance neutral grounding fault current? Can you tell what is the limit?
Limit 10 amps of what I have seen is 5 amps and 10 amps in high resistance ground.
Okay, you are correct. As per our IEEE 142, it is telling 10 amps for a system below 15 kV, and C-gray is giving 15 amps. The basic, this 10 amps, 16 or 15 amps has come from whom? Any idea who is the one who has given this limit?
Maybe the generator OEM.
Yes, you are correct, perfectly correct. The limitation for fault current inside a generator has been given by the manufacturer of this alternator. So the formula is XC. This is XC. Okay. This is
System
RN.
reactor.
This is RN. Okay. So RN for this current to be equal to this current, for resistive current to be equal to capacitive current, 3 times Rn has to be equal to Xc, or Rn has to be equal to Xc by 3. If you ask why these 3 came here, I will show you that when I show you the sequence network.
How do we know the XC of the system, sir?
Xc,
Of the system, how do I know?
to know Xc, you have to know C.
Yeah, so I only know the
What is X capacitive reactance formula?
1 by 2 pi FC.
1 by 2 pi Fc. So what is C? Capacitance, right?
Yes.
Now for a
So now
generator,
suppose
what is the capacitance? Which capacitance it is? It is the winding capacitance.
yes.
To get the winding capacitance, you will get it from the data sheet.
Okay.
So if you are buying a big generator, 100 megawatt, 50 megawatt, etc., the data sheet will have it.
Okay.
And along with that, there is in next slide, I will tell you what where you ask the question, what is XC? There is a separate slide on that. I will explain you in detail. What all capacitance need to be considered, what should not be considered. Okay, I will explain all. And what are the typical values? I'll explain about that. Okay.
Okay.
Yeah. So the resistive component of the fault current IR will be V phase divided by RN. Okay. And total fault current will be IR into root 2. Okay. Now, can you tell what is this?
The voltage build up with respect to time.
You are correct. This is basically voltage building up with respect to time. But why voltage is building up?
Because there is no return. If we have a resistance in the return neutral current, so the voltage keeps on building up because it doesn't have a path to flow back to the transformer.
Yeah. So basically, this is a unearthed system, right?
Yes.
Yeah. So what you can see in the unearthed system. Okay. Now here I have shown a grounding, right? Okay. Actually, this is not there. There is no grounding here. But normally, when there is no fault, this will be at 0. And what will happen? Just like a balloon filled with hydrogen, if you leave, it will flow in the air. No? Same way
Yes.
your system neutral will start floating and it will keep on
Yeah.
changing. And your voltage will keep building like this. It will build like this. And when the arc restrike, it will again build.
Mm.
Again arc restrike, it will again build. But if the system resistance is there, then it will not build like this. Okay. See, basically, charging capacitor, I have showed you the previous slide, that will discharge through a arc. And arc is like a switch. That arc switch is not continuous, right? It is intermittent. It keeps striking again and again. And how many times arc strikes per second? Close to 1,000 times. It may be more than this also, but this is a typical value. So when an arc,
Where does this arc occur, sir?
wherever there is a fault,
Okay. At that place. Okay.
the location where the fault take place, there is an arc
Okay.
there.
Okay. So at that place, the capacitor discharges.
Yes, that is place your current is getting discharged, and that is a switch, like a switch.
Okay.
Opening, closing several times, and conducting current through air.
Okay.
So now, okay, when Rn is less than XCO by 3, we can prevent building up of large voltage. Okay, why? Because see here the voltage I might have built up, but because of my resistance, see, you go for your capacitor theory. When I have a discharge resistor, what will happen? Capacitor will get discharged, right?
That resistor. Yes.
Yeah, same way. I will not allow accumulation of charge in a capacitor.
Mm.
When I don't allow accumulation of charge, where is the question of building up of voltage? Even before my voltage build up, it would have come down little bit. Okay. So that's why the resistance value has to be lesser. If R value is very high, then the current cannot discharge effectively. Now, you asked one question. What is this XC, right? See, you are able to see this capacitance here.
Yes. Yes.
This is the generator winding capacitance. Okay. For the sake of clarity, it has been shown outside like this. And generator is connected to your transformer, the step-up transformer, through a generator circuit breaker. Sometime you may not have GCB in some scheme. It depends, right? Some scheme will have the circuit breaker after unit transformer. So it depends on the scheme made by the design engineer. So if you have a generator circuit breaker, you have this surge capacitance. Have you come across this sort of scheme anytime?
No, sir.
Have you
Sir,
used?
this unit transformer secondary will be solidly grounded, right? That's what you said.
Yes, it will be solidly grounded, and I have not shown it here. You are correct, it will be solidly grounded. Have you used any generator circuit breaker anytime?
Generator circuit breaker only on low voltage I work, sir. So
Okay, see, this go to ABB or GE, any of this website.
okay.
You search for generator circuit breaker there. These
Okay.
you have seen your binocular, no?
Yes. Yes.
In binocular, we have two cylinders, right?
Yes.
Two for left eye, right eye.
Yeah.
Same way, your generator circuit breaker will be in the same arrangement. Only thing is there are three cylinders.
Okay.
It is connected along with the like a pipe. If you are having a big pipe, two pipes. If you want to join one small pipe, we will use to join. No? Same
Ah,
generator circuit breaker will come in between in your bus duct.
mm,
Okay, you can have a search and see that.
okay.
And if you are using generator circuit breaker, there will be what is called surge capacitor.
Mm,
Because when generator circuit breaker open, there will be an arc, there will be a voltage surge. So to mitigate all those, there is a surge capacitance. Okay. So if you are using that, you have to get the value of surge capacitance from your vendor.
okay.
Then do you know transformer also has capacitance,
Yes, sir.
winding capacitance,
But
right?
in high voltage side, it will be very less. No?
See, actually capacitance will be more in high voltage side only.
Okay. Okay.
Okay. So
Okay.
because the capacitance main cause is the insulation.
Okay.
Insulation is more in high voltage, right?
Yes. Yes. Yes.
So there is more capacitance there.
Mm,
So this capacitance value you can get again from the vendor.
okay.
Later on, I will explain you the how, why, which one need to be considered, which one need to be ignored. Now let us see some typical values. You see this zero point 0.2 microfarad. Okay. You see this, it is 230 nanofarad. What is nanofarad?
Further less.
But actually, if you see, 230 nanofarad or zero point 0.2 microfarad is one and the same. Okay. Micro is 10 to the power of minus 6. Nano is 10 to the power of
Right.
minus 9.
9.
And actually, if you see, finally, when I convert to XC in ohms, this is coming to 15,000 ohms or 15 kilo ohms. Huge, right? And you see the capacitive reactance of your surge capacitor, it is 13 kilo ohms. So I cannot neglect surge capacitor. If there is a circuit generator circuit breaker, please find out if it is having surge capacitor.
Okay.
It may have, it may not have. If it has, please get the capacitance value during the calculation.
Mm,
Coming to your transformer winding capacitance will be in picofarad. Pico is how much?
to the power of minus 12.
10 to the power of minus 12, correct. So see the resistance. If I tell in kilo ohms, this was 15 kilo ohms, right?
Right.
This I can tell 136, again
Mega.
3 zeros, unit 10, 100. 1 lakh, 1,36,000 kilo ohms.
1 lakh 36,000 ohms. This is
No, right now it is coming to mega ohms.
mega ohms. Okay.
If I convert mega ohms to ohms, it will be how much? 1.36 lakhs kilo ohms. Okay.
Yes, correct.
Basically, the unit transformer capacitive reactance is how much? 100, almost 1,000 times,
Very high.
1,000 or 10,000 times, almost 10,000 times
Yes.
of the generator. So you can neglect this one because the charging current value will be very, very less given by the transformer. Okay.
Mm, mm,
So what need to be considered, what can be neglected, I have told you. Why we are neglecting, that also I have told you. Okay. We are neglecting because capacitance value is less, capacitive reactance is high, charging current contribution is very less. Okay.
very less. Yeah.
Later I will tell you one more thing. Should now this is connected to a transmission line, right?
Yes.
Should I consider that capacitance or not?
I think it will be very, very high. So I think we can neglect.
Later on, I will tell you.
But sir, if there is a fault in the transmission line, it will come back only to the unit transformer, correct?
You are correct. It will come back to the neutral of the unit transformer.
So that will not affect my generator resistance sizing, correct?
You are correct. It will not affect.
Okay.
But the exact reason is actually whenever there is a delta connected winding, you are seeing a delta winding here, right?
Yes, sir.
Whenever there is a delta, the zero sequence current will not flow. And that is the reason we need not consider anything which is connected to the unit transformer star side. Let's say my transmission line 220 kV line if I'm having here, or I may have a 400 kV line here. I need not consider. Okay. Okay. So what all contribute for the charging current?
Capacitance, winding, cable.
Okay. What all contribute for the charging current? The motors, generator, cable, surge
winding.
capacitors. Yeah. But if you are having a big generator, we don't use cable, right?
Yes.
We are using bus duct. But that bus duct, see, as I told, not transformer and bus duct, both you can neglect. Contribution is very small. Transformer winding capacitance will be very small again, few thousand picofarad. It also you can neglect. I have already showed you the typical value, right? Then you have come across power factor capacitors.
Yes, sir.
FCR panel.
Yes.
Come across it. Where you have used?
Mostly on the low voltage side and 11 kV side.
Okay, mostly you have used on the LV side on the 11. Okay. See this power factor capacitors, they are in star or delta?
Delta.
They are in delta. So because they are in delta, they also don't contribute the charging current.
Yes.
Then anything, I told you, no, anything connected here, this side, need not be considered because of this delta. Okay.
Delta connection.
So that is what I have written here. Equipment beyond delta of the transformer can be ignored. Zero sequence current cannot flow through delta winding. Okay.
Okay.
Then suppose you don't see when you are doing your engineering, you have to design the entire plant. This generator capacitance value you get from the vendor, I told. But vendor drawings you will get only after you place the order, right?
Yes, sir.
And order, suppose order you will place, let's say in January you are doing your design. Your design will get completed in April or May. You will prepare your bill of quantity, specification and all in August, September. Order will be in November or December, right?
Yes, sir.
So how, as a design engineer, how will you then decide the NGR size in January? So you need capacitance, right? Where will you get it from?
Right. Okay, we need some typical values.
Yes, you can assume some typical value. So for generator particularly, you can assume some 45, 50 milliamps. You can assume per MVA of a generator. Okay.
This is the capacitive current, sir.
Pardon?
Milliamps, is it?
Milliamps, yes.
Okay. Okay.
100, if it is, let's say 100 MVA.
Ah,
So 15 to 100 MVA is how much? 15 to 100 is how much?
1,500.
5,000, right?
Ah,
5,000 milli is how much?
5.
5. So it will be 5 amps for 100 megawatt. If it is 600 megawatt, 600 megawatt, it will not be 30,
6.
will not be 30 amps. See, actually, when you go for very big generator, no, what you do is you, instead of taking 50, you take 30 or 36.
Okay.
So let's say 600 megawatt, 36, 3.6, 3.6 into 6 is how much? 3.6 into 6 is 18. It is close to 20 amps, right?
Yes, sir. Yes.
But actually, the maximum current will not be more than 15 amps. So you can go down further down. So when you make assumption, no, use a higher value for lower rated generator. Use a lower value for higher rated generators. Okay. Generator winding capacitance will be in microfarad, and surge capacitor is used, that should be considered. Okay. So now, any doubt till now?
No, sir. Okay.
In the function of neutral grounding, in the causes of fault, in the type of grounding, in this damage energy, then the concept. This is the basic concept of HRNG. This is clear, right?
Okay. Yeah, clear, sir.
This is very important. Then cause of over voltage, briefly you have understood, right? Why over
Yes.
voltage happens in a system. Then charging current. What is charging current?
Yeah.
Charging current basically means what? See, you how a capacitor works, you are clear.
Yes.
Two metal plates, between them there is a insulation.
Later.
You know that concept, right?
Yes, sir. Yes, sir.
Yeah, when you apply DC across it, there is no flow of current. But when you apply AC across it, current will flow. Why current will flow? It is not because current flows through the insulation. Current will never flow through insulation. Insulation does not conduct current. Instead, what will happen? Charge will get accumulated at one side, and because of induction, charge will get accumulated at the other side also. And when you
Yes.
reverse the polarity of the voltage, charge will flow back to the system. And that is how current flows in a AC system, in a capacitor. In reality, current will never pierce through your insulator.
Capacitor.
Insulator is having electron. Those electron will not conduct current like a conductor. Okay.
Yeah.
The concept of current flowing in a insulator capacitance is basically accumulated charge will go sit inside the plate, come outside the plate. That is how it happens. So now that is, so in all our electrical system, whether it is a generator, whether it is your cable, whether bus duct, transformer, everywhere we have conductor, and around the conductor we have insulator, right?
Yes, correct.
So this conductor and insulator combination acts like a capacitor. And whenever there's a capacitor, there's a charging current. There is, and that current continuously keeps flowing. But normally that current will not flow through your resistor. The reason is IA, IB, IC, the sum of all three will get cancelled out in the neutral. Normally system is balanced, right?
Yes.
Because system is balanced, IA plus IB plus IC will be equal to 0.
Under normal condition.
Normal condition. Okay. So you have understood the concept of charging current, and you understood how to calculate the value also, right? From
Sir, now one question, sir. Now suppose we do the earthing conductor sizing for this, but only till the generator only till the transformer. The
Okay.
maximum current, the fault current that my ground conductor will ever carry is say 10 amps only, right?
Okay.
It is not going to be like what we did in our solidly ground system where we have lot of circuits. To reduce the fault current, we have lot of parallel path for the conductor. But here my fault current is very, very less. So my grounding conductor size also can be less.
You want still your question, whatever you told that ground current will be very less. Yes, you're correct. But when we design the earth mat, we design for the actual system fault current in kiloamps. Okay.
Okay. But practically it will never be that current. No, sir.
Practically, what happens when there is a fault? See, the same earth mat is interconnected for this transformer also, right?
Yes.
See, this neutral is connected here, and this neutral also is connected to the same neutral. Not the neutral, same earth grid. Earth grid is common.
Grid.
My entire plant earth grid is common.
Yeah.
I have a common earth grid throughout my plant. Okay. So because of that, my earthing system is always designed. I'm telling you what is done normal in the industry.
Okay.
My earthing is a common grid throughout the plant.
Okay.
There is not that generator earthing and that my transformer neutral earthing, then body earthing. All I have to separate, nothing like that. I have to
Hmm.
make a common earthing throughout the system. And that common earthing system has to be designed for the system fault current. Okay.
Okay.
Not for 5 amps, not for 10 amps.
Hmm.
Whether it is 50 kA or 25 kA, whatever is there in the SLD, as per that I have to do. Clear?
Yes, sir.
You are correct. When the fault take place here, only 5 amps will flow
Hmm.
here. But when fault take place here,
Yeah.
kiloamps will flow. And since
Yes.
it is a common grid, I will design it for kiloamps.
Okay.
So you are clear about this also, what all contribute for the charging current, right?
Yes. Yes.
Okay. So for now we will stop here.
Okay.
So evening 6 o'clock is okay, right?
For me, it is okay, sir.
Yeah, 6
Whatever
o'clock.
time you are okay.
Yeah, join now today. And
Hmm.
hold on 1 second. Let